So, now not only can we have two waves mixing, so we had a good picture of the scenario that we are working with here would be as follows. So, here is a medium, here is a chi 2 medium, and we have essentially a wave we have a beam at omega 1, omega 2. So, we could then have beams come out as a consequence of nonlinear processes, right. Let me just write this down the following way. We could have 2 omega 1 to omega 2, we could have omega 1 plus omega 2, omega 1 minus omega 2, and vice versa. We could have had omega 2 minus omega 1. Also, one of them will be is greater than the other, and we do not have negative frequencies. So, we have to pick either of them. So, if I assume omega 1 is greater than omega 2, I need to consider only one of these and the DC term, right. So, these are the consequences of the second harmonic process, right. These are the consequences of the second harmonic process, but nothing stops us from envisioning an n wave mixing process where we could have, chi n, we could literally have n beams. I mean, n seems a little bit of an exaggeration, it needn't be, but we could in principle have n beams interact in a medium, but the key thing is they should interact, that is in a certain volume of the medium. It is the experimenter's job to make sure that all the n beams are focused down with a good degree of overlap, right. So, you get a signal, nonlinear signal from the overlap region where the intensity varies and so on and so forth, right. The intensity at the focus of a beam, I mean, okay, let us put in some arrows here too. All this will lead to a certain level of experimental sophistication. So, these processes, however, are called n wave mixing processes. Like what is shown here is a good example. Again, the subscripts have moved out a bit, but please bear with me. So, we have omega 1, this may we can say that a photon of omega 1 is absorbed and a transition is made. Note that these states denoted by dashed lines are not necessarily existing energy levels of a system. Okay. So, these are so called virtual states. This is the quantum mechanical picture. It is the easy, in some sense the easier way of understanding these processes which work by energy and momentum conservation. So, this is the energy conservation part of it. So, then you have omega 2 interacting with the omega 1 beam in the presence of this medium. So, we first a transition to a virtual state is made, another transition to another dash, that is virtual state, gets made when the omega 2 photon is absorbed, and a transition to a third higher lying virtual state is made when omega 3 is absorbed by the medium. So, this is omega 1, 2 and 3. So, the system has climbed 3 steps on this energy ladder, on this energy landscape. Now, if you had omega 4, it could well be that we do basically, if in this scenario we have considered an omega 4 which is omega 2 plus omega 3 is equal to omega 4. We have just considered an example of this type, right. It could well happen that in the medium the process of the next frequency generation is subtractive, that is omega 1 plus omega 2 plus omega 3 minus the omega 4 happens, and say there is an omega 5 which is equal to omega 2. So, this could then lead to an upward transition to again all this to virtual levels. Remember, all these transitions are to virtual states or levels, right. They do not exist in reality in terms of having a finite lifetime, right. So, now the point being that all these waves have mixed omega 1, omega 2, omega 3, omega 4, omega 5. When we add or subtract these frequencies, what we are doing is we are mixing these waves. So, this is the difference between say something like adding, we may associate adding with interfering or beams just interacting in a medium. If 5 beams interacted in a medium, let me dare to sketch only 3, and if the medium of interest was say linear, then indeed the amplitudes here can add up, indeed they add up, the amplitudes of the waves always tend to add, but then they are also oscillating fields, right. But after the beams interact at the output side, we still have omega 1, we still have omega 2, we still have omega 3. There is no change in these 3 frequencies, and these beams walk off as if nothing has happened in this medium. That is, beam 1 at omega 1 has not modified anything of beam 2 or modified anything of beam 3. If omega 1, 2, 3 were to be equal, we would have seen an interference pattern over here. We could well have seen an interference pattern in some medium, whatever may be the case, right. We could have seen fringes if we satisfied conditions for observing interference, but if they were not of the same frequency, omega 1, omega 2, omega 3 are not degenerate, they have different frequencies, we would not, there would be interference, but we would not be able to observe it with our slow detectors as we had spoken about it. But the point being that even as such, if we had a medium within the purview of linear optics, there would be just coexistence of the beam in the volume where they overlap. Whereas, in nonlinear optics, there would not be just mere coexistence in the regions where they overlap, in the volume they would mix. Mix, the word mix corresponds to frequency addition. This is the key difference. Coexistence, overlap, mixing, frequency addition in the case of a nonlinear situation. This is the consequence of linear interactions. Okay. So, the dashed states are virtual levels. So, now how do we understand or represent this 5 wave mixing process, right? We have 5 waves, in fact there are 6 waves if you include the signal itself. So, we should have called this a 6 wave mixing, the process that we have depicted over here. okay, you could well say that there are 5 sources, primary waves, and the 6th is generated. So, could also call it 5 wave, but the convention is to include the resultant consequent wave also, and this is a 6 wave mixing process. Okay. Now, all of this is still written in terms of the polarization field P, which is now P is of course epsilon naught times, it is a mixing of the 6 waves. So, say omega 1, omega 2, omega 3, the corresponding E's, and the upward the omega 1 plus omega 2 plus omega 3, there is a plus omega 5 and there is a minus omega 4. So, whenever we have a minus sign, the corresponding frequency gets subtracted out and we have the complex conjugate of that particular field appearing, and there should be a corresponding chi to this process. Okay. And this would result in a P which essentially oscillates at the frequency omega signal. We can now easily see that for this process the signal frequency is omega 1 plus omega 2 plus omega 3 minus omega 4 plus omega 5. It is a very high order nonlinear process. 5 initial waves are mixing to reveal a third wave. Okay. So, that is an n wave mixing process. Now, let us come back to second harmonic generation. Okay, my sketch has gotten a little messed up, but the message is still conveyed rather. The message is about applying conservation laws to this situation. Okay. In every physical process, energy and momentum must be simultaneously conserved. So, conservation is the key. What does this imply for us in terms of these wave mixing processes? So, in every physical process, energy and momentum should be conserved, right. So, we can say that we seek energy momentum conservation. Yes. So, energy conservation is obvious. We go in with 2 photons, a photon each of, here the picture, first of all the picture of a photon is what we have been using more or less, naturally, although we are talking about propagating fields which is composed of many photons, right. So, we go in with 2 beams of frequencies omega 1, even a single beam in a nonlinear, in a medium which has appreciable nonlinear response can behave in a sense of 2 overlapping beams of omega being present there, or you can deliberately split the beam and have 2 beams of omega . 2 beams of omega 1 interact in a medium with appreciable nonlinearity. It is good to think about this in terms of photons. So, 2 photons of omega 1 are simultaneously absorbed by the same atomic unit, okay, and a photon with frequency twice omega 1, which is what omega signal is. Omega 1 is twice omega 1 is omega signal. We call this the signal. the second harmonic is the signal, omega 1 is sometimes or often referred to as the pump. You pump and you get the nonlinear signal out, isn't it? So, this is a sort of 2 photon process. The virtual level should have been here. My virtual level was virtually displaced. So, please bear with that inaccuracy in the cartoon. I should check why this is happening, which I will do in the meanwhile. So, second harmonic generation is essentially energy conservation, but then momentum also must be conserved, isn't it, for the beam. In terms of the picture, in terms of say frequency domain, if z is the propagation direction, we had omega 1, omega signal, is twice omega 1. Of course, the vertical axis is E of t, right. So, now we know that the momentum of a photon, okay, so this is pump, signal. So, the momentum of an electromagnetic wave and or each photon essentially is h bar times k, right, or in other words k is the beam momentum, whereas h bar k is the momentum of a single quantum of light. Momentum of a quantum or a single quantum of light. Okay. So, now we add two quanta, we added them energetically correct, but then this in the process of doing so, we must also conserve momentum. Momentum we know has direction, k vector is propagation direction for the beam or for the photon. So, when two k's add up here, okay, then the momentum of the signal photon, the momentum of the photon with frequency omega signal, or which is the same as 2 omega, okay, should be k signal, where k of course is omega by C naught multiplied by the refractive index of the medium at the corresponding frequency. That is the magnitude, this does not convey anything about the direction. Now, if I had a single beam and I generated a second harmonic from that, a single beam interacting with a crystal, this is not the scenario I have sketched here. If we had say a single beam interacting with in a medium, let us say I already called it a crystal because we need crystal for second harmonic generation, as we will see, rather than amorphous media. To observe and have appreciable second harmonic generation, we need crystals. But the point being that what comes out as a consequence of the second harmonic generation is a beam at a different frequency. So, there is a blue beam which would emanate from this crystal. It is not that the pump would be totally converted to the second harmonic, that is not true, I am exaggerating the case here simply to make a point. Okay, so we have omega signal and k signal for this beam. Okay, omega signal, k signal for this beam. Now, the point therefore being that there must be a relation between k signal and the two k ones. In this geometry, this is equivalent to two photons of omega 1 k 1 being absorbed and a photon of omega signal, which is twice omega 1 being emitted. So, these should come about, right, in the process of conserving energy and momentum. Momentum conservation is the key thing now. We understand energy conservation in that the frequency gets converted. What about momentum conservation? What about momentum conservation? So, that is the question we are going to answer in this lecture and maybe part of the next. The point here being, if second harmonic is generated, we understand that energy is conserved, because the energy of a single quantum of light is h bar omega. So, h bar omega 1 plus h bar omega 1 gives h bar omega signal. H bar omega signal is twice h bar twice omega 2 or twice h bar omega 1. So, we have conserved energy naturally in generating second harmonic. How do we conserve momentum? Do we conserve that at all, or do we have the case for a breakthrough of something like violating this? Okay, we dare not even think of such a possibility, but whatever it may be, this is a point to consider. Okay. So, if the two pump beams are collinear, that is omega 1 and omega 1 in the single beam second harmonic generation scenario, which is depicted in the figure which I have hand sketched, and the little schematic here. If omega 1 and omega 1, that is k 1 and k 1 are collinear and parallel, then k signal has no choice but to have only the component which is parallel to k 1, as is shown here. Agreed? It has no other choice. It cannot, this component of k signal is not allowed to exist, because momentum cannot be conserved then. Momentum is a vectorial quantity, right. So, therefore, but what is k? Therefore, now in the scenario where all the three are collinear, okay, what is the deal? What must happen? What must happen is that the magnitudes must match now. The magnitude of k 1 is omega 1 by C naught times the value of the refractive index at omega 1. Note this carefully, this factor carefully. Now, k 2 is likewise omega 2 by C naught, sorry, omega signal by C naught multiplied by the value of n at omega signal, right. This is equal to twice omega 1 divided by C naught multiplied by n at twice omega 1. No, I cannot take this 2 outside of this parenthesis. This simply says I am looking for the value of the refractive index at a different frequency. Evidently, if the medium is normally dispersive, for normally dispersive media, n at twice omega 1 should likely be greater than n at omega 1, yeah, for normally dispersive media. We just saw that a little while ago. So, now what does this conservation, what does the conservation of momentum mean for this sort of a scenario? Okay. For this sort of a scenario, the conservation of momentum means k1 plus k1, that is twice omega 1 by C naught n omega 1, that is k1 plus k1, equal to twice omega 1 C naught n at twice omega 1. So, oh no, remove, cancel out the common factors. This leads us to n at omega 1 should be equal to n at twice omega 1. Aha, but what about this normal dispersion? Is this valid? Let us see the same. I have written it down on the slides too. These two things cancel out, right? And we seem to say, oh, when second harmonic generation happens, the refractive index of the medium at the pump frequency and the refractive index of the medium at the signal frequency is equal. Can we force this? Does the medium know that my life is dependent upon generating the second harmonic, so it somehow grants me this wish? No, it is an inanimate medium. It is our job to figure this out somehow. But for normally or anomalously dispersive media, if it is anomalous dispersion, the inequality would have just been the other way around. There is absolutely no reason to have these two values to be equal. Can these values be approximately equal? Just a small difference, right? Would it be okay if n omega 1 is some approximately equal to n to omega 1? Can I give myself a concession? But in physics there are no concessions. But remember that these terms appear in the phase of the equation of the wave. N appears in the phase of the wave. Small numerical differences in the phase, essentially, I mean, by small what do we mean? Whatever we mean by that, are not tolerated. In phase things are a lot more delicate, right. So, none of this will matter, right. So, simultaneous conservation of energy and momentum, the conservation of momentum particularly would necessitate that we now find media where the refractive index at omega 1 is equal to the refractive index at twice omega 1. Alright, is this even possible? We laid out a nice framework for generating the second harmonic. Maybe it is not possible to generate the second harmonic because momentum conservation is never possible. Maybe it is never possible to generate, it is just maybe a theoretical possibility if you wish. Okay, maybe you can argue that I will try and figure out a medium where the two refractive indices are somehow engineered to be equal. Okay, possibly, maybe can I do a meta, some meta material trick? Maybe I can find a meta material where this is always possible or is possible for a pair of frequencies omega and 2 omega, maybe, may not be. but it seems for naturally occurring or easy crystals and media and whatever, this is never going to happen. Yeah, now we are jumping ahead. It is not trivial therefore to generate second harmonic, the second harmonic of any medium. So, it is, we have worked ourselves into a spot, right, into a tight corner, where first of all to observe appreciable second harmonic, we need appreciable electric field. We saw this yesterday, that we require beams with reasonable intensity. The pump intensity nominally should be something like 10 to the 8, upwards of 10 to the 8 watt per centimeter square. 1. So, you need a laser. Now, you bought the laser, you got the crystal or whatever nonlinear medium that my friend here thinks will work. So, get everything, but then nature says no, you are violating momentum, you are not conserving momentum. So, I will not, you will not see any second harmonic. So, it seems that we have worked ourselves into a tight corner. Is there a way to wriggle out? Is there a way to rescue ourselves from this scenario? That is the question we have to ask, and let us see if there is any hope at all. If I just steadfastly followed all the arguments so far, I would end up at this juncture, okay, on this slide with a terrible disappointment that we have no hope of generating the second harmonic, unless we do something quite clever, which is kind of what Franken and co-workers first did, right. So, for the case of second harmonic generation, if I magically or otherwise ensure that this hallowed condition n at omega 1 is equal to n at twice omega 1 is equal, then we would be set to have accomplished phase matching. Why phase matching? Because refractive index is phase modification. So, we have if this condition were to be somehow achieved, we would have achieved phase matching, the condition necessary to observe the second harmonic. But how do we do this? Otherwise, it is like interference. Two waves, light waves with frequency omega 1 and omega 2 respectively, whose frequencies are not necessarily equal, do interfere when they coexist in a certain volume of space, but we cannot observe the interference, because we do not have detectors which with responses of petahertz frequencies or bandwidths of petahertz that we would require. So, we fail to capture it. So, likewise in the case of second harmonic generation, without the phase matching being done, so you cannot observe the second harmonic, or for that matter high order harmonics. This is the key thing. How do you observe the high order harmonic? Even there phase matching is both important and needs to be achieved. So, let's take a pause for a moment and absorb this very critical and crucial development, that for observing a harmonic generation, we need to establish phase matching. Okay. Well, I will just add a nuance to this, that we will quantify all this in reasonable terms very soon. Although I am being a bit picky in demanding that in this case twice K1 be exactly equal to K signal. In real life, just as with frequencies we we do have a certain amount of detuning and stuff like that. In real life we could well have a small, or we can have a scenario where the delta k is not necessarily always 0, it could be very close to 0. We will see about this soon. So, a small phase mismatch can exist, but not a substantial phase mismatch. After all, this is phase, right. So, what matters is if the wave propagates a length L in the medium, delta k times L, the propagation length, leads to a certain phase mismatch between the two parties, the cause, the pump, and the effect, the signal, right. A certain amount of phase mismatch is inevitable for many reasons. Okay. But barring that, or rather in the ideal scenario, these phases must be matched, or we take it in the spirit that we need to make our best efforts to match the best phase, or assure the least mismatch of phase, right. So, that is the experimenter's job in doing harmonic generation, right.